Well, I might just do some of the housekeeping things. We'll wait a couple of minutes just for people who are finding their way in. Zoom's a new platform for a lot of people. So, yeah, sometimes there's a bit of a learning curve about working out how to launch it and where to find all the different elements. So we'll go through a few of those today as well. So this is the Year 8 lesson, so just make sure you're in the right class. It's like the first day of school where kids turn up to the wrong place, but that's okay. So this is going to be for Year 8, and our focus this lesson is going to be on real numbers, and that's chapter 1 from our Mathspace Year 8 book. So I'll talk a little bit about me. We've still got some people coming in, which is great. This is me. My name's Erin Gallagher. When I was a teacher at school, kids used to affectionately call me Miss G. And yes, I don't mind if you want to refer to me as Erin or Miss G, whatever's comfortable for you. I've been at Mathspace now for, I think, 7 years-ish, something like that. But I was a teacher in schools for a long time before that. So I've taught in high schools, but I've also taught anywhere from grade 3 right up to university level maths. And I've spent a lot of time teaching teachers how to teach maths as well. So one of my absolute passions is making sure that students can see and feel that they can do it, like just to really embody that sense of success, if you like. That's really important to me. And I do believe that everybody can. A lot of people say, oh, I'm just not a maths person, but I think if it's approached the right way, everyone's got the capacity to learn the things that are essential. So, and that particular snapshot of me was last year. So if you've been overseas, you might recognise that as the Grand Canyon. That was a great trip. So some sort of simple housekeeping things firstly. So again, I'll just reiterate, this is going to be covering the Year 8 curriculum, and we can't do everything in the 1 hour that we've got. I can't cover the whole course in 1 hour a week. That's why in school you'd have math class a couple of times a week, because that sort of needs that time for you to get into it and to practice things and to ask questions. But I do want to try and give you enough of an understanding of the chapter so that you can continue to learn on your own or with the support of your teacher in your school. So as I've said before, we will follow the Mathspace curriculum, and if you don't have access, then you can ask your teacher for access to Mathspace. We will record the class, so that's a very common question, and that will be made available I think by tomorrow afternoon, as well as all the slides that I use and any links that I use to things like GeoGebra applets or any files, etc. They'll also be available for you to look at later. I will use a poll or two to get a sense of your understanding at different points. That is a feature within Zoom. And if you've got, if you're using like an app, if you're not running Zoom in the browser, then that will just pop up on the screen. If you are running Zoom in the browser, then unfortunately you won't see the poll. So if you don't see it, then it might just be the method by which you're using Zoom. We will have a chat, and there is a chat. You might have found that button already. There's a couple of people who have thrown some hellos and good mornings into the chat, which is great. Reminder, just like in class, you know, don't speak loudly, don't be rude. We want to be polite and treat each other with respect. So I will use the chat. It'll give us an opportunity to engage and be able to talk with each other. So I'll ask you some questions and you'll be able to throw in your responses in there as well. Feel free to chat to specific people. You can address your chat to us as panelists, or you can address it to the whole group. When I do ask for your input in the chat, try and make sure that everybody can see it. Otherwise, you may end up speaking to one person, and then you won't know why you're not being heard. There's a Q&A feature as well, so have a little look around the screen, see if you can see the Q&A button. That'll ask a panelist, which is me, a direct question. I will try and pause at different points to check if there's Q&A that's worth covering as we go, but otherwise I'll definitely leave some time at the end of each lesson to go over some specific questions. So that's a really good opportunity. If you've had a look at this work before you turn up to this class, because this is kind of like a bit of a review session, and you know you've got a couple of really keen questions that you want answered, you throw them in there and then we'll be able to get to them by the end. So behind the scenes, we also have Renelle. And so Renelle's another great teacher. She's behind the scenes there. She's helping me out. She's pressing some buttons and monitoring the chats and stuff like that. And Renelle taught science and maths for 12 years in the US before she came on board with Mathspace. And a little bit like me, her focus as a maths teacher has been to really build confidence so that they have no fear while learning new topics. So rest assured you're in good hands with the two of us here to help and answer your questions today. Okay, so let's just go over some of those aspects of Zoom that we want to be able to utilize. So make sure you can see the chat section. If you could all just sort of throw a little bit of a hi or a good morning or something in the chat, then we'll know that we've got everyone sort of being able to find the chat, because you don't want to be left out of the conversation. If you can't quite see it on your screen, if you move your mouse around, sometimes the little menu bar will pop up so you can see where the chat is. Awesome. Yeah, hi Karen, hi Kirsten, hi Ross. Good morning, Paul. Good morning, Laurel. Good morning, Shahana, that's great. Hi, Gary. So the other section that I mentioned that we want to make sure you can see is the Q&A. So remember, the Q&A is where you can ask the teachers a question directly. So it's not a public chat forum, it's just where you can just throw in a question. I just want to make sure you can see it. There'll be an option somewhere on your in your menu to see Q&A, and make sure you can find that, and that way you can ask a question if you need to. Now, there's also a feature in Zoom called annotation. I'm just going to turn that on for now. I want to see if you can find the annotation tool, because I want to use that a bit later. The annotation tool is where it gives you the capacity to write on the screen. In fact, we could all write on the screen together. So it's like having a big whiteboard in the room and having everyone come up to the board with a pen. Now, the annotation tool is sometimes a bit hidden. Again, it's in the little menu button. So if you hover around, you find the menu that pop up. There might be a little more menu with 3 dots. And within there, you might have an option for annotation. See if you can find that annotation tool. And sometimes it has a little pen icon, and you should just be able to draw on the screen. Oh, yes. Sorry, Paul, if you're on the phone, you probably won't have that tool. I think that's more of an app for actual desktop or laptop users. Just wait a bit longer and see if anyone else can find it. If we don't get enough of that, then I'll probably skip that part of the lesson, because we'll just see if anyone has access. And so again, just a reminder, you're looking for an annotate tool that will have a icon. It's not available on all different browsers and things like that. So that's okay. We can try again next time, I suppose. So if you're using a desktop version and you're using it through an app, Kylie, then there would be a little menu that will appear when you move your mouse around on the screen. But if you're using it in the browser, I'm not familiar with that. I'm not going to be able to help you there, I'm afraid. Oh, there we are. Renelle found it under view options at the top of your screen. So if you go right up to the Zoom menu, go view, see if you can see it there. Okay, looks like it might not be something that people have. That's okay. All right, so I'll just clear that. Okay. And now, as I mentioned before, sometimes a poll will pop up on your screen. But as I mentioned before, it won't happen if you're using the browser. So we won't, well, I should have thought about that, having a little test poll to see if you can see it. But anyway, we'll get to the poll a bit later, and we'll handle some of those questions then. So, okay, just close that. Okay, so let's think about where we are in our learning. So this, as I said, is going to be a focus on chapter 1. It's on real numbers. And that's what we're going to be doing this week. And then next week, which we'll be doing the same time, same day, will be I focus on chapter 2 for percentages and income. So the way to make the most out of this would be to definitely have a look at that work and the content of that work before you come. That way you'll have clear questions or gaps or things that you want to clarify. It'll make a bit more sense, because as I said, we've only got an hour, we're going to be moving a little bit fast. So hopefully this isn't the first time you see this sort of content. So I might point you to some places where you can get help at more depth as well with this content. So if you go to wootube.mathspace.co, the address is in that top left corner there. You might have heard of a great teacher called Eddie Wu, and so he's done like thousands of videos of his class when he covers all of this content from 7 right through to year 12. And what we have is a big catalogue that's mapped all of his great videos into our book. So for chapter 1, you'll be able to navigate in through wootube.mathspace.co. You'll be able to navigate in, you'll be able to find chapter 1, real numbers, and you'll see that for all of these different sections, there are a number of videos. So if you were having trouble with section 104 on rational and irrational numbers, there's 11 videos of Eddie Wu doing some of those small things. So and that's a great place to go for some of that more in-depth specific learning materials. And that might be something that you want to do for next week. So next week we're going to be doing percentages and income. So you could navigate in, you could watch some of these videos on percentages and income, do some questions either from your own textbook or from the Mathspace work, and come pretty prepared. Okay, so we're going to start. I'm going to tell you a bit of a story. So I've got some pretty basic animations here, but the idea is the story. So let's just try and follow along. So we want to talk about real numbers and what they are. So I'm going to take you on a bit of a journey. We're all going to be goat herders, and we're going to be living on the top of this really lovely mountain range. And it's your job every night to count the goats in from the big open paddocks into the paddock that's closest to the house where they can be safe. Now, this is in a day where maybe we don't have formalized numbers yet. We just know we have goats. There's no sort of formal language around numbers and values and amounts and quantities of things. So how could we keep track of how many goats we have? In fact, this is true. This is how, when you go far enough back, people kept track of things. So one method is each time the goat comes into the yard, what you do is pick up sticks. So as you bring in your goats, you pick up sticks, and you keep picking up sticks till all the goats have come in from the field. And now you have a bundle of sticks. Now we don't name how many sticks that we have in our hand. We just know this is how many goats that I have. And you can go back home, or you can go back to your family, and you can say, I've done it. Here are the goats, and you're having a good night's sleep. And the next morning you come down and you take your bundle of sticks and you go back down, you open the gate and the goats go out. And so every time they go out back through the door, you put the stick back down. So we keep putting the sticks down and put the sticks down until all the goats have left the field. Now, of course, if you've got a stick left over, something's gone bad overnight and you know you need to go looking. And that's sort of how things could be kept track of before we had a concept of number, before we had a way of naming things or being able to count them. The next development was then to actually have words and language to support this. So instead of picking up sticks, we just used the words, but that meant we had to have a common language. We had to learn what these numbers were, and we had to make sure that we all learned them in the same order. There was no point just having names for numbers if a 6 for me meant these 6 goats, but a 6 for Anel meant 2, like in my language. So we had to make sure we had a common language there. But the same process would apply. You'd go down to your field at the end of the day, you count your goats in. So you'd start counting and you just go 1, 2, 3, and you just count your goats in. And then you'd end up with a value or a quantity. In this case, we have 6 goats. Same process, you go home, you come back, and the next day you can count them back out. So you're 1, 2, 3, 4, 5, and 6. So there's our 6 goats. The next development was to, I understand that sometimes the quantity of 0 was important. What if I had no goats? How could I represent that? And this is really interesting to note that the value 0 and the number 0 actually was a very late development in our history of number. So we've been counting goats. And of course, if you want to count something, then that starts with the value 1, because you don't count things if you don't have them there. So in that way, it kind of makes sense why 0 was a bit of a latecomer to the number party. So there, we had to identify that 0 was a thing, that we now have 0 goats. We have no goats. And so the idea of having the number 0, a word for the 0 and a way to represent that was important. Okay, so we're going to continue with our goat farmer theme here. So imagine now that every weekend you take this beautiful journey. You go down the valley, you cross the bridge and into the farmer's market, and you take some goats with you. And you talk to the flour farmer who's there and you say, I have goats and I would love some flour. And the flour farmer says, okay, well, I can't really just do a trade. Like, to me, I feel like my flour is valued at a higher rate than your goat. I have to grow the seeds, I have to harvest the seeds, I have to process them into flour, I have to grind them down, and then I have to carry these heavy flour bags to the market. And what's decided is, well, in that case, let's go with half a bag of flour for one goat. And that works really well. So every day you can make that lovely trip down the valley, across the bridge and into the farmer's market, and you can do a trade for half a bag of flour for your one goat. So this introduces this idea of having parts of a whole. It wasn't a whole bag of flour, it was half a bag of flour. How could we measure that? What could we call that? So then we needed a language and a way of representing parts of a whole. And of course, you'll recognize parts of a whole as being fractions. Then things get tough. We head into a drought, and your goats, your milking goats, are no longer producing milk because they're on hard times. But hopeful, you still head down the village, head down the valley, across the bridge and into the farmer's market, and you come to the flour farmer and you say, I don't have a goat to offer you today, but could I still have a half a bag of flour? And you've developed a great relationship. They're very lovely farmers, and of course they want to help you out. So they say, sure. And this now introduces the idea of negative numbers. You now owe this flour farmer a goat. You didn't have one. So you're sort of in the negative. You're in the red, if you like. So next time your goats are back doing well and you post the drought, you're going to owe this flour farmer a goat, and then you'll be able to clear that debt. So we've introduced this idea of a way of tracking debts, which is a little bit about where negative numbers come in. Okay, so I'm going to tell you the same story. We're going to put some more formal language around it. It's still, whilst it's not entirely a true story of the development of number, it's quite representative of a theory about how the use and the development of different types of numbers came into being. And it's very similar, in fact, to the way that you will have experienced the development of number through your schooling years. Have a look at that. We start off with this idea of counting things, starting with the number 1 and counting on 1, 2, 3, and so on. Just like as you're counting your goats in and you're picking up sticks, or we turn to using actual numbers. So you're counting from the number 1. From a very young child, probably before school age, you start counting. You start counting things that you have. And you have to learn the order, because the order is really important, because we've got to know that the value of 3 means the same for me as it does for you. So that's the natural numbers, and sometimes they're called counting numbers, and they start at the number 1. We introduce now the idea of whole numbers. So whole numbers, you see this is a big circle around the natural numbers, because whole numbers are all of the numbers that we've just talked about, the 1, the 2, the 3 and onwards, but also with the addition of the value of 0. So whole numbers are starting at 0. I have no goats, then I have 1, 2 and 3 and onwards. So whole numbers are that whole set, if you like. We introduced the idea of 0 pretty much straight at the idea of school, even though before school most kids just sort of start at the value of 1. Okay, what happened next? Well, then we introduced the idea of fractions. Fractions came into being at around year 2-ish. We start talking about having parts of wholes, and we start having this idea of being able to represent them symbolically as well as with words. So again, it's the same sort of story with the goats. We were swapping for half a bag of flour. in fact, you'll see the fraction circles around the outside of all of these. It's around the outside of the whole numbers and the natural numbers, and that's because these are fractions as well. So how is the natural number 2 a fraction? Well, that's because it's 2 wholes, so it'd be 2 over 1. So all of these can be written as a fraction, 0, 2, and then all of the fractions. So we're starting to build types of numbers and build our knowledge of numbers that we can use. Certainly by the time you sort of move through primary school, you start doing things with fractions, you start counting with them, you start finding different types of equivalences, you start recognizing that 2 quarters is the same as half. You might even start doing things like adding and subtracting fractions together. Now things get pretty tricky. We start adding more and more. So certainly in year 7, there's an introduction to what we call negative numbers. Now negatives is this idea of this little tiny line at the front of the number. And there's 2 ways we can represent negatives on this particular diagram. You'll see we've got integers, which are the whole numbers, but the negative versions of them. So we've got -1, -2, -3. The integers is all of them. So it's all of the negatives and all of the positives and the value 0. So imagine a big number line with just the marks at the whole numbers. That's the integers. But we can have negative fractions. So I want to put this out here in this fraction section. And in fact, during year 7, we often start changing the reference of fractions and start including this idea of being a rational number. So that's a new word that gets introduced in high school. What's a rational number? Well, in fact, you'll see it's in the exact same places where I had the word fractions. A rational number is any number that can be written as a fraction. So it's all of these numbers. They can all be written as fractions, whether they're positive or negative, whether they're whole numbers, they're all rational numbers. And if it's not rational, then it's irrational. So rational numbers cannot be written as fractions. So these are some examples of irrational numbers. They can be negative as well, but they're often a bit messy, even though they look kind of cool. Some of them just have letters and there's these square root symbols, but if we wanted to evaluate them on a calculator, that would be a bit messy. It'd be very long, unwieldy. So on the topic of irrational numbers, let's just pull out a common misconception that students have is that all square roots are irrational, which is actually not true. What about the square root of 4? Well, we can evaluate the square root of 4 to be the answer 2, which is actually a natural number. So not all square roots are irrational. Just some square root numbers end up being irrational. Okay. This is all encompassed in what we call real numbers, which of course is the topic of this week's chapter, real numbers. So basically, this whole chapter was about working with any of the numbers that appear within this circle. They can be rational, written as a fraction, irrational, can't be written as a fraction. They could be positive or negative. They could be negative rationals. They could be negative irrationals. They could be whole values, 1, 2s, 3s, or they could be negative whole values and be part of the integers. So this whole chapter is about understanding these types of numbers and working with some of their operations. Okay. So let's have a look at this sheet here. And I want to ask you a quick question and maybe throw it in the chat. I was going to do an annotation activity, but because we couldn't get that working so far, let's go to the chat. Keeping this diagram in mind and thinking about all the different types of numbers that you've done in school so far, what numbers don't I have on this picture yet? So just throw in some answers into the chat there. What sort of numbers are not here? What do you think I've missed, for example? Yeah, some great answers there. Laurel and Kylie, decimals. Absolutely correct. Decimals seem to be missing. Paul's correct too. Percentages. Where are they? And they're all different types of numbers that we've been doing. Decimal numbers in Australian curriculum started about year 6. So you've certainly seen them before. And in fact, decimal representation you see from far earlier than that, because we all deal with dollars and cents. And Paul's correct too. Percentages, they seem to be missing too. So what's really important to understand about decimals and percentages is that they are other representations of the numbers that are already there. So they're not a number type on their own. Decimals and percentages can be both rational and irrational. So let's have a look at some of these decimal numbers in detail. So there are basically 3 sort of main types of decimal numbers. They can be one of these 3 things. They can be terminating, which means they stop. There's a certain number of decimal places and then that's it. You can write it exactly as it is and as it appears. So there's some very simple examples of terminating decimals. So just remember, terminating means stop. The other type of number is recurring decimals. So recurring decimals are numbers that recur like a single digit, like 99999, and these dots mean and on forever. So just keep going on and on and on and on and on. Or they can repeat in a pattern. So we've got 32, 32, 32, 32. And then there's even more complicated ones, 125, 125. In fact, any sort of sequence that repeats in a decimal that goes on and on and on, we could kind of call that a recurring decimal. And then there's the others. So these are non-recurring, non-repeating decimals, and that's some of those other things that you saw in that irrational picture. So the square root of 2 goes on and on forever, and we know that it actually doesn't repeat anywhere. So it's not a recurring decimal, it's not a terminating decimal. Yeah, exactly, Luke, that's great. So then we've got pi. So it's sort of like non-recurring, non-repeating. And well, here's the thing actually about pi. For the millions of decimal places that mathematicians have calculated pi to, we haven't found that it repeats yet, but we haven't proven that it will never repeat. So that's one of the great things about science, is sometimes we discover things many, many years later and go, oh, what do you know? But as far as we know at this moment, pi does not recur and does not repeat. So yeah, that's exactly right. Like 31.2 trillion places. So it's a lot of decimal places. You'd think that if you've gone that far, it's unlikely to all of a sudden start repeating, but you never know. From that very next place, if it's a 1, it might go 1, 4, 1, 5, it might start again. We don't know yet. Okay, so what do we know about these 3 types of decimals? Well, these first 2, the terminating and the recurring, they all form part of our rational numbers. And these others, they're in the irrational numbers. So here we are. So all of those terminating and repeating decimals will form part of the rational numbers, and those other ones will be irrational. Okay, so we're going to have a quick poll now. And the question is quite simple. It's which of these numbers is the odd one out? Now, this is our first time that we've done this, and like we just discovered with the annotation tool, it didn't work for everybody. So we'll see how this goes. There's a series of 4 numbers that should pop up on a poll for you. They should pop up on your screen. Now, we know that you won't see the poll if you're running Zoom in a browser. You should still see it if you're on a mobile device. I did a Zoom webinar last week and I was able to see the poll on my phone. And all I want to know is which is the odd one out. So there are 4 values there. There's a square root of 1. There's minus 0.2. There's the fraction 2/5 and the fraction 1/9. So people are putting their answers in there. That's great. We'll keep that open a bit longer. There's a few more people in the room. We'll see if we can get a few more responses. If you can't, if the poll hasn't popped up, then it's quite likely that it's not going to. It's not something that you necessarily need to find. It normally just pops up on the screen in front of you. That's great. We've got some great answers coming in. Fantastic. So keep going a few more. Just turn on my annotate screen. I didn't make a slide for my discussion here, so we'll see what we can do. We'll just draw on the screen and see how this goes. So important to note too, so whilst as all our schools and classrooms are moving to more remote learning, so everyone's having to learn new things. So if your teachers are going to be supplying you with work, likely they've had to learn something new in the last week to be able to do that, some sort of an online platform or some sort of if they're going to run any sort of chats or classes or lectures, they might have to use Zoom. So this is actually our first Zoom, or my first Zoom webinar as a teacher too, so it's something that I'm also learning. So okay, so here we go. I'll just change that to a better colour so we can see it. So which is the odd one out? Okay, so let's stop that poll and we'll see the results. The results should come up on your screen, what people have said. So the overarching winner there was that 1/9 was the odd one out, but there's some people who thought the square root of 1 and minus 0.2. In fact, it could be that any of those numbers are the odd one out. So I'm going to give you a moment now in the chat. If you can just justify your answer, why did you choose the thing you chose? In fact, there's no wrong answer. 2/5 could also be the odd one out. So I'll just pretend I picked that one. So yes, Laura's right. There are different answers, and that's the whole point. So let's see if you can justify why you've chosen that answer. Just throw that in the chat there. That'd be great. Thanks, Anna, getting us started. Yeah, excellent. That's great. A justification for 1/9, Paul. Yeah, exactly, Laura. That's great. So there's only one negative number there. Also, it's the only decimal representation that's provided. Perfect, Ross. Yep, 1/9 is the only recurring decimal. That certainly comes into what Paul mentioned about the first three can be rational. Yeah, so that's exactly right. So there's a whole range of numbers there, and they're all unique for their own specific reasons. So we've got the square root of 1. It could be the only square root number. It's the only whole number, as was mentioned earlier as well. Minus negative 0.2, the only decimal, the only negative. Written as a fraction would be 1/5. Written as a fraction, the square root of 1 would be 1/1, which could make 2/5 the only non-unit fraction. So that could be unique for that particular reason. 1/9 is actually a recurring decimal, and we'll do an exploration about recurring decimals soon. And the other three can be written as rational. Okay, so that's great. Sorry, there we are. Close that. Okay, so on to this specific chapter. So what I really wanted to sort of hammer home, if you like, for the first part of this class today was this idea of understanding how all these different types of numbers are connected in, how they've been developed in time, and how we've developed them through your school life. And then we can talk specifically about what's expected in year 8 from this. So what we have here is a bit of a snapshot from the chapter. So these were the key things that were covered in this week, or that we are covering in this week. So the real number section is made up of 5 sections, mostly around, so remember, multiplying and dividing integers. Remember, integers are the whole values that also have negatives. So we looked at how to multiply and divide those. It's an extension from year 7 where you would have been adding and subtracting integers. Then there's some mixed operations, which of course is all of the operations, multiplying, dividing, addition and subtraction. There's a section on fractions and decimals, and in fact that's operations involving negative fractions and decimals, because you've been adding fractions and decimals in year 7 in a positive landscape. And then we moved on to this idea of rational and irrational numbers. So I've started talking about those this morning. Remember that rational number is any number that can be written as a fraction. So that's generally the easiest way to remember rational. Can I write this as a fraction? And then there's also a component in year 8 about being able to multiply and divide numbers that have indices or powers. And so that's at the end. I'm just going to check the time. Okay. And that'll guide how long I spend in each of these sections. Okay, so we have multiplying and dividing integers. So 101 from the textbook. There's a whole heap of different rules about whether the numbers are positive or negative when you multiply and divide, but there's 2 key things you need to remember out of this whole chapter. If you're multiplying or dividing the same signs, if they're both positive or if they're both negative, then the answer is positive. So you can see that here, both positive, both negative, the answer is positive. If they're different signs, answer is negative. So that's the key point here. Same is positive, different is negative. So I'm just going to go to the textbook. So this is the Mathspace textbook. This is what we're following. Again, if you don't have access yet, then certainly ask your teacher. They can get it to, access to you for free. So we have multiplying integers. I'm just going to scroll down. You'll see all those rules that I've just talked about are there on the page that I've just summarized. I'm just going to go down to the bottom to these questions here. And we're just going to try these 2 problems. Just so I can talk through exactly what we're going over here. This is sort of the way you would approach problems like this. So it's an evaluate. So it's just a work out the answer, if you like. For most of these, you'll need to have some good sort of multiplication and division skills. You can do that mentally in your head, or you can use a calculator if you're in a, I'm just opening my calculator now. So you can have a calculator handy as well. Of course, the thing about digital remote learning is often no one's going to know if you're using a calculator. And I was always a really big fan that if you needed the calculator to engage in the work, then please do so. At the same time, it's good to try and still build up your skills and being able to handle some of these computations mentally. Okay, so here we go. We've got 11 times bracket -8. So what does this mean? The brackets here around the -8 are just holding that negative with the 8. Okay, so the brackets are not asking you to do an operation or a calculation. It's just saying, hey, here's a number, -8. And the operation itself is a multiplication. So we've got here 11 times -8. So the way I always handle these computations is I think about the computation first. So here I have 11 times 8. I know that 11 8s are 88. And then I check the signs. I've got a positive and a negative. So remember what I said before, different signs mean the answer is negative. So this one is -88. Okay, let's have a go at another one. Again, in this case, we can see that we've got brackets around that negative. That's just holding the negative with that number. So we've got -36 divided by 4. Okay, so firstly, I'm going to look at the computation. 36 divided by 4. I know that 4 9s are 36, so the answer will be 9. And now I check the sign. I've got a negative and a positive. Different signs means the answer is negative. Okay, so that's the key thing, remember. Different signs, negative. So you can handle the computation as you would normally. Just you can kind of pretend like the negatives aren't there as long as you apply that layer of understanding about what's happening with the negatives. Of course, if you're using a calculator, most calculators have a negative button, so you can actually do the calculation exactly as it appears. -36 divided by 4. Okay. The next chapter was on next section in the chapter was on mixed operations with integers. So that's just doing, I'll show you in the book actually, multi-step problems involving addition and subtraction, multiplication or division with positive or negative numbers. I would like to get to the end of the chapter that gets more difficult, so I'm probably just going to skip over this one for now. But you can see the sorts of questions that are involved here. So in this first one, I would do the multiplication first. So with regards to our order of operations, you know, the brackets will do first. So I've got 9 times 6 is 54, but I've got a positive and a negative, so it's -54. And then I would have to add the 5. So there's a whole section of questions in that section of the book that you can practice multi-step problems with positive and negative. So I really encourage you to do that if you haven't already done enough practice at school this year. Okay, 103. This actually combined a couple of key concepts together. Firstly, we want to multiply and divide fractions and decimals. We want to be able to do those things. And we also want to be able to do that using negatives. So we'll do some stuff regarding the fractions and decimals with multiplication and division. That layer of using negatives is just that layer over the top again. Same signs, positive, different signs, negative. So that doesn't add a layer of complexity. It just adds another level that you need to consider in your response. Okay, so let's go to 103. So here's the lesson on 103, fractions and decimals. There's some examples. Okay, here we go. We'll do these two here. Now, as I showed you before in the questions section, there's heaps of questions that you can use to practice all of these different concepts. So in here, there's a whole lot more. We're just going to pick a couple to go over today. Okay, multiplying fractions. Okay, so this is an evaluation. Now, again, if you've got a calculator that handles fractions, this could be quite simple, but most schools would want you to have a level of being able to do this like manually on paper. So let's have a look at what this means. When we're multiplying fractions, here we have 5/7 multiplied by 8/11, and there's some negatives involved as well. The general idea with multiplying fractions is to consider the numerators and the denominators as separate sort of calculations. So what I'm going to do here is I'm going to write, we've got 5/7 times 8/11. So the top line, what I want is 5/8. And I want to put that all over 7/11. Now, of course, I'm not finishing this because I've got to consider the negatives yet, but I want to show you what I'm thinking in my head. Firstly, we're going to multiply the numerators, 5/8. So that's 5 times 8 is 40. Then I'm going to multiply the denominators, the bottom numbers. So 7 times 11. So that's going to be 77. And then we have to consider the negatives. So we've got two signs that are the same. They're both negative. Same signs, positive. So I don't need to add a negative answer there, negative sign there, because when both signs are the same, the answer is positive. So we can enter that in. It's funny because when it takes a while to respond, I still go, oh, did I do that right? See, it happens even when you're my age and you've been doing this for 40 years. Okay. So that's multiplying a fraction. I'd love to do a dividing fraction before we move on. So let's find a dividing fraction. Actually, this would be a great one too. I'll do a few of these. Sometimes fractions can be tricky, so it's worth seeing a few examples. So let's do that one and that one. Okay, let's do those fractions first. Okay, so same idea as before. So let's think about the numerators, the top pieces, and then the denominators and the bottom. So we've got 2/7 multiplied by 9/5. So on the numerator, I'm going to think about, I'm not going to press enter yet because I'm not finished, but I just want to write down a bit about my thinking here. So I've got 2/9 and the 7/5 on the bottom. I mean, the 7 and the 5 is the denominator on the bottom. I'll do these calculations first. So multiply the top pieces. So 2 times 9, I'm going to do the 18 there. And the 7 times 5, 7 5s are 35. And now I'm going to consider the signs. So I've got positive and a negative. Different signs, answer is negative. Okay. That was quicker. All right, let's do a division. Now, division's really quite tricky. I could spend a whole hour's lesson on understanding the idea around dividing fractions. We don't have time for that, but certainly go and watch some of Eddie Wu's videos on dividing fractions. Fantastic. And certainly talk to your teacher. He might be able to put some examples into videos for you. But for now, we're just going to move forward with what the end point would be, what you need to be able to do. So we've got here is 3/7 divided by 5/4. So I'm going to start by writing down that first fraction, which is 3/7. Dividing fractions is actually pretty tricky computationally if I leave it like this. But as we've just seen, the multiplying of fractions is something we can handle, because we can multiply the numerators and multiply the denominators. So what we're going to do is turn the division into a multiplication. Now in mathematics we say multiply by the reciprocal, which is a fancy word for saying multiply by the same fraction flipped upside down. Okay, so we're going to go multiply by the same fraction flipped upside down. So we flip 5/4 into 4/5. So this is what a mathematician, a textbook would say is multiply by the reciprocal. So you flip it upside down. Okay, so that's our first step. Just going to enter that in. We've got a tick, so we're on the right track. Now we know how to do the multiplication of the fraction. So just like I did before, we consider the numerator. So 3 times 4 is 12. And the denominator, 7 times 5 is 35. Nearly pressed enter then. Okay. So remember, try not to look at this left side. Try and just look at that right side. 3 times 4 is 12, and 7 times 5 is 35. Okay. So it's dividing fractions. It's this idea of multiplying by the reciprocal. Okay, let's do another one of those, because I know that they can trick some people up. You might need to practice these. We'll do one more. Okay, here we are. So we've got a negative this time. It's being held within the brackets. So I've got the fraction negative 5/9. I'm going to turn this into a multiplication. So what we're going to do, we want to multiply it by its reciprocal, which means multiply it by the same fraction flipped upside down. So multiplied by the reciprocal. That's my first step. And my second step is to do the numerators and the denominators. So the top pieces and the bottom pieces. So I'm going to go 5 times 7 is 35. 9 times 8 is 72. Don't forget to consider the sign. So here I had a negative. So this is negative 5/9 times positive 7/8. So they're different signs. Different signs means the answer is negative. So in this case, you could do the exact same question. You can probably do it in full on your calculator. If you've got a scientific calculator that you use at school, they'll have a fraction button. So you can just use, 5/9 and times 7/8. They'll have a negative button, so you'll be able to put in the negative 5/9. Even on the normal mobile phone calculators, when you turn them sideways, they've got a little fraction button as well. Oh, not on the normal calculator app, on a special calculator app you can download. Sorry. Okay, so here we are. So turn the division into multiplication and then multiply by the reciprocal. Okay, so here we've been talking about multiplying and dividing fractions, but the dividing of the fractions really turns into a multiplication with that one step. And like I said, with that extra layer of check the signs. If there's negatives involved, you need to make sure you consider that. Is the answer positive or negative? Half of this chapter was about decimals, multiplying and dividing decimals. So they're the same sorts of things. So I'll just open up just a couple of those. And we'll do some dividings. Okay. The thing with decimals is that they're pretty messy to do by hand. You end up doing a fair amount of like algorithmic type calculations on paper. We can certainly do this for this question, 3.2 times 9.8. I don't have a pen yet, but it would look something like this. So 3.2 times 9.8. And you go off and you do your calculation, you'll end up with a couple of lines and you've got to put your decimal places back in. Most schools that I've worked in for this level certainly allow you to use your calculator for this. So being able to multiply decimals like this is really about being able to use your calculator effectively and correctly. And one big aspect of using your calculator correctly is to make sure you know what sort of an answer you're expecting. So let's consider this. Let's clear that. We'll go again. So 3.2 times 9.8. So let's look at what we're expecting our calculator to give us, because if you don't know what you're expecting, then you don't know if you've typed something wrong on your calculator, and that's really important. Calculators are great, but they only do what you tell them to do. So if you've typed the wrong thing or you forgot to put a decimal point in, it'll do the calculation and it'll give you that answer, but you need to know if that's the answer that's right. Okay, so let's have a look at how we could get an idea about what we'd expect from this before we put it in on our calculator. So 3.2, let's call that close to 3. 9.8, let's call that close to 10. So for this answer, we'd expect an answer somewhere around 30. If we get an answer that's way out of that, then we've probably typed it in a bit incorrectly. We've probably missed a decimal point or made a typo with the actual digits. So I'm going to get out my calculator. I'm going to 3.2 times 9.8 gives me 31.36. So you can see our estimate was pretty good. It's a little bit more. Good to go. Okay. The next one again. So now we've got it. You can see there's a negative there. There's a negative inside the brackets. So again, we've got 3.6 times negative 6.9. So let's put our layer of thinking over the top first. So the 3.6, let's call that close to 4. The 6.9, let's call that close to 7. It's a negative, so we'll call that negative 7. Now using our whole numbers and multiplying by integers, we can see that 4 times 7 is 28. And that with different signs, so the answer is negative. So we'll expect an answer somewhere around the negative 28 mark. So let's get out our calculator now. 3.6 multiplied by 6.9 is 3. See, I typed it wrong. 3.6 times 6.9. Here we are. So that's 24.84. And of course, it's a negative because that value is a negative. Okay, it's pretty good. Same thing with the decimals. So we're going to run out of time, so I'm going to move on, but you do the same thing. Think about what the answer could be, type it in on your calculator and check the signs. So in this case, it's going to be a positive answer. In this one, it will be negative. Different signs, negative. Okay. Let's go back to our slides. We've got here rational and irrational numbers. So this is a pretty important section. What is a rational number? We talked about that at the beginning. Identifying recurring or terminating decimals. So we talked about that as well. You need to understand that language and what they are. And then you need to be able to know how to write recurring and terminating decimals as fractions. And if you can write it as a fraction, then we know that we can write it as a rational number. So there's heaps of questions in the textbook, of course. I'm just going to go through 2 examples here for you. So 0.125 is a terminating decimal. It stops. All terminating decimals can be written as a fraction by using place value, by identifying, well, this is in the thousandths column. So that means it's over 1,000. It's that simple. Every terminating decimal can be written like that. This number here, 0.66, so it ends in the hundredths column, so I can write that as a hundredths fraction. So that's very simple. All terminating decimals you can just write as a fraction using the place value, the tenths, hundredths, thousandths, 10,000ths, and so on. Okay. What about these ones? I told you before that the recurring decimals were rationals, but I didn't sort of explain why. And this is a pretty tricky concept, but it's actually pretty clever. I remember when I was a kid in school being really amazed about how clever mathematicians were when they came up with the way that they can show how to write this as a fraction. So let me just show you the screen and then I'll talk a little bit about them. So, well, all of a sudden I've got algebra there. I know, don't freak out, we're okay. What we have here is a constructed statement. This is something, you know, in mathematics, there's a lot of rules that mathematicians come up with. You know, they come up with the rule for the circumference of a circle. You know, they say it's 2 pi r, and they give it to us, and we all go, oh, great, we can find the circumference of a circle. And we use that rule, we throw in the numbers, and we get the answer. Well, this isn't kind of like that. What they're doing here is they're constructing a specific method to make something happen. It's like they're being, you know, clever magicians. If you ever watch those magicians on TV, what they've done is they've staged the things that happen in 3 steps time so that you'll be amazed when they happen. And it's exactly what mathematicians are doing here. So they're constructing something so that the magic can happen. So let's just see where the magic is. Here we have 0.6666 recurring, goes on forever. What they've done is said, well, let's have 10 lots of that. So remember when we multiply by 10, all the digits move around the decimal point by 1 value. We end up with 6.666666, and onwards it goes. And then they say, well, if we just take away the 1 lot of the 0.6, then you're going to have taking away the 0.66666 and onwards. And this is where the magic happens, because when we do that subtraction, all of those 0.666s, they disappear. So it's like they were laying the groundwork, weren't they? So they were, so we'll set it up like this, and then in a couple of steps time, bang, disappear. That's pretty clever. And now we have a very simple 1-step equation. We can solve that for x. We can divide both sides by 9. We can simplify the fraction. And we can see now that there's the recurring value of 0.66666 recurring is a fraction. Therefore, it's rational. Okay, this takes a little bit of getting used to. I really encourage you to go and practice a few. Every sort of recurring and repeating decimal has a different pattern that you need to work out, but it puts you in the magician's hot seat. It makes you be the magician. Okay, so you get to decide, how can I make these decimals that go on forever disappear? Because that's the goal. If I can do that, then my calculation becomes simple. So that is my challenge for you for the next week, is to go off and make sure you can be the magician in this particular scenario. Okay, we've got 2 minutes, so I really want to answer some questions. So what I'll do is I'll leave you with this slide. You'll get the slide, you'll get all the links. It's about multiplying and dividing with indices. I'll show you those GeoGebras. They're really fantastic. So the multiplication law for indices looks a bit like this. Let's just do 1, and then you'll see how the applets work, and you'll be able to go off and have a bit of a play. So let's just reset this. Okay, so what we have is this idea of 9 to the power 7. Remember, an indice is something that you multiply it by that many times. So here we have 9. I have 7 of the 9s. 1, 2, 3, 4, 5, 6, 7. Next to that, we have 5 of the 9s. And we're multiplying them all together. So the idea is, well, how many 9s altogether? Well, you can see that there are the 7 we had plus 5 more. The whole thing is 9 to the 12. Okay. So you'll be able to have a bit of a play with this. You'll be able to see, get a real feel for how this works, and then come up with the rule. Okay, so there's a rule in the textbook. It's good to really understand where the rules come from. So you can see here that we had 7 and 4 more, means altogether there was 11 of them. So please do go and have a look at those. They'll really help with your understanding about why the rules work. Okay, sorry that last bit was pretty rushed, but like we said, we're all learning to see how much we can fit into it, and with technology and things like that. So let's switch now to the Q&A component. I'll just quickly check the chat, make sure no one's sort of had anything to say there. Okay, let's just have a quick look at the Q&A. So throw any last minute questions you've got there. I don't mind if you run a little bit over time. I'm happy to answer a few questions. If you've got somewhere to be, absolutely fine. Thanks so much for joining in. So remember, next week is about chapter 2. So it's percentages and income. So you might have already done that, or you haven't yet. So definitely have a look at that chapter in advance. You can ask your teacher for a login, or have a look in your own textbook, get a feel for, you know, your year 8. You might probably already have a year 8 textbook at home. Have a look at the percentages and income section, and we can go over some of those questions. Okay, so there's a couple of questions in Q&A. Let's go there and have a quick look. Okay, so open questions. Is 0 positive or negative? See, is 0 positive or negative? Well, I think it depends on where you go. Even the internet will be confused on that one. Generally, people consider 0 to be positive. We don't generally write the negative sign on the 0. Negative 0 and 0 are the same thing. So that's why some mathematicians say that it's neither, because they're equivalent. So great question. Let me see if I can come up with a better answer for you next week. I might start next week with something like that and see if I can put something better together for you. Leave that one with me. Paul's asked, what's an adaptive quiz? So Paul, you probably saw that on the page when I was sharing. There was a thing about doing an adaptive task. So within Mathspace, you can do a task adaptively, which means it'll select questions based on how well you're doing. So if you've been finding them pretty easy, you'll move through and get harder questions. If you've been, finding them a bit challenging, then you'll stay and you'll get some easier questions. So an adaptive quiz adapts to what you're demonstrating your knowledge to be. And Mathspace can do that for you. So you'll be able to go in and then just practice what you need. So, there might be some areas where you only need to do 5 questions because you're pretty good at it. And there'll be other areas that you find challenging and you might need to do 20. But that's what the adaptive nature does. Yes, Kylie, the video will be saved. It'll be on that webinar page for Mathspace. I believe if you've registered too, you might get a link to that, but certainly check out the webinar at Mathspace link. It'll be up within about 24 hours, so you can check tomorrow afternoon. You'll be able to watch it again, or share it with people who weren't able to be here today. Fantastic. I think that's it. There's how many people are online? So today, I think our numbers, we had about 60 something registered, and those that turned up today, I think was maybe about 20 something. So that's about standard, about a third of the people would turn up. And it's holidays for most people around the country. So actually, I'm really stoked that we had about 20 people today turning up on their holidays. So I don't know how many of you are teachers or how many of you are kids, but thanks so much for turning up. So that's fantastic. Excellent. Okay, well, I think we're done, everybody. So it's so nice to have you. Hope to see you again next week. We're doing percentages and income, but certainly if not, hope this was useful to you. Thanks, everybody. Okay, everyone. So we ran out of time. So this is the bonus add-on. You've waited to the end of the movie cinema and all the credits have finished rolling. Bonus time. So we're going to go over 104 and 105 again, just to get a little bit more depth and show you a few more things that we sort of rushed through at the end because we ran out of time, just because I was having so much fun developing the whole concept of number with you. So I'm going to share my screen and we're going to go to 104 and 105 again. Okay, so where did we leave off? So was about rational and irrational. The real key component from this is to be able to identify and really understand that a rational number can be written as a fraction, and we need to know how to write some decimals as fractions, and can we write what sort of decimals as fractions to be able to identify them as rational. And then those that can't be written as a fraction are irrational. So in 104, rational and irrational numbers, I'm just in the question section. I'm just going to pick a couple of questions here to do as some more examples for you. So firstly, something like this one. It's a nice simple one. Here's another one. That opened, yes. Here's another one. Here we are. Okay, now we're going to write some fractions in decimals. So we're going to go the other way. And then we've got some recurring ones, so that's pretty important. So we're going to do a few of these so you get a bit of a feel for the process. Like I said, we're writing these recurring decimals as fractions it's really putting you as the mathematician in the magician's hot seat, but we'll get to those. That's the fun bit. Okay, so where are we? Here we are. So it's going to write some fractions as decimals. Okay, so there are some things that we should know. We should know the equivalent fractions and decimal representations for what we call benchmarks. Benchmark fractions are things like 1/2, 1/4, 1/10. You should know those because they become very useful. So let's just go over some of those benchmarks. So 1/2 as a fraction and as a decimal, yes. So 1/2 is 0.5, and you need to pretty much remember that one. It's a really important one. Another one that you need to be able to identify is 1/10 as a decimal. Now 1/10, that's kind of a bit easier because we have a tenths decimal place, and 1/10 of those is exactly the same. So 1/10 as a fraction and 1/10 as a decimal. Other benchmarks that you should know are things like the quarters, so 1/4 and 3/4. So 1/4 as a decimal is 0.25. We can talk about why that is. Maybe I'll just mention this one briefly. Let's think about what 0.25 is when we say that. It's 25 hundredths. So that's 25 hundredths. So we go 25 over 100. So it's 25 of those hundredth size pieces. And in fact, then you might recognize that 4 25s are in 100, and we can see that these two are equivalent fractions. So it's a little bit about where that 0.25 comes from. But there's certainly benchmark fractions to decimals that you should be pretty comfortable in being able to just write down. But what if you don't yet? What's a way I can do this? So if you don't know that yet, then what you can do is you can use your calculator. We need to understand that this fraction line is one whole, like this is saying sort of divided by, 1 divided by 2, 1 divided by 10, 1 divided by 4. So on your calculator, you can just type in 1 divided by 2 equals, and you will get 0.5. That calculator, the way of being able to do that using a calculator works for every single fraction. Just use it like a division. And we'll do that on the next question. Okay, here we have 5 over 9, 5 divided by 9. So if I type that on my calculator, let's see what happens. So I'm going to go 5 divided by 9. What I get is this. I'm going to write it down, what I see. That's what my calculator's saying. It's not quite right. If I turn my calculator sideways, so I'll show you, see if I can show you. Here we are. So there we are. And now if I turn it sideways, oh, it gets longer. That's a really key thing to be able to say, oh, it actually keeps going and going and going. And this 6 on the end is just, it's just the calculator trying to round it off. If I can't keep going and going and going and going forever, it's still not quite right. Like I'm kind of there. I've got a half tick, but I have to write it as a recurring decimal. I have to use that recurring symbol sign because wherever I stop, that's not exactly right. If I stop there, what I've written is a terminating decimal. A terminating decimal can be written as a fraction in a different way, and it's not going to be the same as 5/9. So what I need to do is I need to indicate more clearly that this goes on and on and on forever. And the way we do that is using the recurring decimal sign. And there's a button on Mathspace where I can get that. If you're just using a pen and paper, then you just put the line over the top. So there we are, writing as a recurring decimal. But using your calculator shows you what is recurring. Often you've got enough decimal places on your calculator to be able to see that, and then you can write it down. So again, it's about using your calculator effectively and knowing how to interpret that correctly to write the correct answer. Okay, let's do another one. Here we have the fraction 3/7. So I'm going to do that as a recurring decimal. So again, I'm going to get my calculator out. 3 divided by 7. This is what I get. This is tricky. 0.428571443. What's going on there? It doesn't look like it's repeating yet. Got a wrong tick. I don't know. So I'm going to turn my calculator sideways. See what happens now. 428,571. Oh, now I see. It's 428,571. And then that's the bit that's repeating. 428,571. And that's the bit. So what I need to do, I could write that down, but not quite right. Like I've got to write it as a recurring decimal. What I've written there terminates. That's not right. So I'm going to find the repeating piece. It's this whole thing, 428,571. That whole piece is repeating. So I put that all under the repeating digits. There we go. Okay, so that's fractions to decimals. So we can use our calculator to be really clever about how we do that. Okay, now I want to do some writing fractions, writing decimals as fractions. So we're going to go the other way. So anything that terminates, we can write using that place value. So anything that terminates. So this is 7. Here we are. I'll draw for you. 7 in the tenths column. Okay, so that means the fraction is 7/10. 7 in the tenths column. Oh, I need to write it as x. There we are. 7/10. Okay. All right, let's have a look at the next one. Again, this is a terminating decimal. It stops. And what I want to do is work out what decimal place is that. Okay, so I've got the tenths would be the one. The next column would be hundredths, and the next column is thousandths. So this is, let's have a go. 125 thousandths. Then we learned from the last one, we need to write it as an x equals statement because we're like x equals. So then we have 125 thousandths. Let's have a go at that. Fully simplified is the instruction. Here we are. So 125 thousandths is correct, but we're not fully simplified yet. How can we simplify that? Well, to simplify fractions, we need to find common factors. How do we do that? Well, what number goes into both 125 and 1000? Well, 125 does. We may not be able to get to that straight away. That's pretty tricky. What about 5? Let's start somewhere simple. How many 5s in 125? So I could write this as 5 times 25. How many 5s in 1,000? Did you get it? It's 200. Okay, so that's correct. So it's still the same value. Now I can cancel out the 5s. So I can cancel that out. Leaves me with 25 over 200. Still not fully simplified, but I'm getting closer. The numbers are getting smaller, cancelling out some common factors. Let's go 5 again. How many 5s in 25? 5 of them. How many 5s in 200? What do you think? Well, there's 20 in 100, so there's 40 in 200. Okay, we're getting there. You can cancel out these common factors. Okay, 5 and 40. I can take out another 5. Okay, 1/8. It's a bit more tricky just because we had the simplification to do. Now, if you've got a scientific calculator, you'll have a fraction simplifying button. 125 over 1000, press equals, and it'll tell you that it's simplified to 1/8. So you can skip those manual steps if you're using a calculator. Okay, let's go. Write x as a fully simplified fraction. So what we see here is we've got a recurring decimal. So we need to set up a bit of that statement. So we need to be the mathematician here, okay? So at the moment we know that x is, oh, my writing's not so great here. I'm going to have a pen to write next week. So 0.33333. It'll keep going on and on and on and on and on forever. What we want to do is get that, get rid of those decimals. So what happens if I have 10x? So I'm going to go 10x is, I'm going to move all of those digits around the decimal place. So I'm going to have 3.333 recurring, okay? On and on and on it goes. This is, now we're getting somewhere. I can see now how I can set the stage so that those decimals can disappear. So what I'm going to do is going to go 10x minus x equals 3.3 recurring minus the 0.3 recurring. Okay, now why did I do that? Because I'm setting the stage, so I'm going to be the magician. When I do the subtraction, I've got 0.333333 minus 0.333333 disappear. When I do that, subtraction, here we go, we're getting there. Now I can make that 9x, 10x minus 1x is 9x. Fantastic. Now I've got to do one simple division. I can divide both sides by 9. What you do to one side, you must do to the other. That leaves me with the value of x on this side. Fantastic. And now simplify with 3/9. So 3/9 is the same as 1/3. There we go. So remember, this bottom bit is just some manipulation. Okay, that's not the decimal. That's not the real tricky bit. The tricky bit was identifying how to set the stage, how to make all those decimal points disappear. All right, let's do one more. Here we have a more tricky one, 0.166666. So let's just write that out. It might mark it as wrong, but I just want to show you what I'm talking about. This is 0.1666. That's what's happening here. Okay. What happens if I just times that by 10? Then the number will move around the decimal point. I'll get 1.66666. That's fine. If I subtract one from the other, oh, it's not quite so nice, is it? Because there's still this 1 here. It's not setting the scene as nice as I want yet. What if I do 100? That gives me 16.66666 and onwards. Okay, now that all of these decimal extensions are the same on the 100x and the 10x, that's what I'm going to use. So what I'm going to do is I'm going to wave my mathematician wand. And I'm going to use those two. I'm going to use the 100x and the 10x because on both of those, the decimal extension is exactly the same. When I subtract them, they're going to disappear. Okay. So this gives me 16.6 recurring. And I can subtract from that the 1.6 recurring. Why am I doing that? Because I'm in charge and I want those decimals to be able to go away. So now I can make those decimals go away. Which leaves me with two more simple subtractions on both sides. So 100x minus 10x is 90x. 16 minus 1 is 15. And now I divide both sides by 90. And then I have to simplify the fraction. So how many 15s are in 90? Well, there's 2 in 30, which means there'll be 6 in 90. Okay, so I'll go back over this. The key thing here was to keep trying different values of 10x or 100x, or sometimes you might need to try 1000x until you get 2 of those values where those decimal extensions will be the same. As soon as you find that, subtract one from the other, the decimals will go away and you'll end up with a small, simple equation to solve. Okay, so there's certainly a lot of questions you can practice in the chapter there. Now, the last section we didn't get much time on is the 105. Oh, we saw this slide. Here we are. Okay, now this is the multiplying and dividing with indices, and I left you with some GeoGebras. So let's go over those and really understand what's happening with these indices and how we can use that to answer questions. So there's 2 key sides here, and this is the same with most mathematics. There's the rule that we can give you, that you could use, that then you could repeat. There's the understanding of the rule. Now, if you understand the rule, then you're going to be able to do a bit more than just use the rule in the future. You're going to be able to apply that in different situations. You're going to be able to extend it to different types of numbers or into algebra and things like that. So let's look at understanding what's happening with indices, what's happening when we're multiplying them and when we're dividing them. And then we'll look at some questions. So there are 3 GeoGebra links. I've already got them open. Okay, the first one is just about indices. Okay, just understanding what indices are. Just want to have a look here for you. So the meaning of indices. So here we have 8 squared. So it's 8 times 8. I'll move this up one more. 8 cubed. I've got another one. So there's the 3 of the 8s there. 8 to the power 4. I now have 4 of the 8s there and onwards. So that's what the index is, right? This little number tells you how many times is in that multiplication, how many times that number's there. I'll go back the other way, 8 to the 5, and I go down by 1, so I'm dividing that by 8. So now I've only got 4 of them. I take away 1 more 8, I'm down to 3. I divide by 8 again, I'm down to 2. I divide by 8 again, I'm down to 1. What happens next? I divide by 8 again, I end up with 8. So hold on one second. End up with 8. That's not a good pen to use. Let's try this one. I end up with, here we are, sorry about that. 8 over 8. What is 8 over 8? Dividing this by 8 gives me 8 divided by 8 gives me 1, and that's no power. So anything to the power 0 is this kind of situation where we've divided it by itself and you're down to 1. Okay, so let's go from here. 3, divide by 8, 2, divide again, 1, divide by again, 1. Anything to the power 0 is 1. Okay, so there's 2 key things there. What is 8? What is anything to the power 0? And what is the index? What is it telling us? Okay. So that's what an index is. You can play with this yourself. You can see you can change the numbers, you can change the powers, get a real feel for what's happening with the indices. Okay, multiplying indices. What's happening here? Let's use 2. Okay, so my blue one, 2 to the 8, my red one, 2 to the 5. So I have 8 first, remember? 8, 2 multiplied by itself 8 times. We have 2 multiplied by itself 5 times. How many altogether? I have 2 multiplied by itself 8 plus 5, 13 times in total. Okay, let's change it. Let's go this way. Okay, here we have 6 to the power 4. So I've got 4 of them, and then I have 9 of them. So altogether, I have 4 plus 9, I have 13 of them. This is exactly where that rule is coming from. Let's go again. Okay, we have 2 of them, 1, 2. I have 6 2s, 1, 2, 3, 4, 5, 6. Altogether, I have 8 2s. Okay, so when I'm multiplying by indices, what's happening here? I just end up with more of the same. So I can just add them. That's like a total. How many in total do I have? 6 plus 2 was 8. So that is the rule, and you'll see the rule stated on the book. We developed the rule. The rule uses some letters. Most mathematics rules have some sort of letters to identify things. Here's the rule. A to the power m times a to the power n is at the power of m plus n. So there's 2 key points. Base has got to be the same. Both 2s. They were both 3s. Both 6s. Doesn't matter. As long as they're the same, okay? They've got to be the same. Then you can add them. If they're the same, you can add them. So we've got 2 here, 6 there, altogether 8. Okay. Now dividing. Let's have a look at the dividing. Just going to switch this around. Okay, so let's look at 6 to the 8 divided by 6 to the 4. Firstly, bases have to be the same. They're both 6s. Or they could be both 2s. Or they could be both 3s. They have to be the same. Okay, now let's have a look. Let's expand that out. Let's have a look. So we've got 3 times itself 8 times. Remember, dividing is like a fraction, over 3 by itself 4 times. Okay, now let's cancel some things out. These are all the same on top and bottom. That's the same. Anything divided by itself is 1. Okay, so we have 3 to 4, 3, they're the same. So they cancel out. What does that leave us with? Just these 4 at the end. So when I write that as an indice, what I get? 3 by itself 4 times. Okay, let's see a different one. Undo this, undo this. Sorry, I've got a fly buzzing around. Okay, here we go. Let's do something like this one. Okay, we've got 8 to the 6 divided by 8 to the 2. 8 to the power of 6 divided by, so if it's divided by, we can write it as a fraction, divided by 8 to the power 2. Let's expand that out. So here we have 8 to the power 6. We divide it by 8 to the power 2. Let's see what we can cancel. We can cancel out anything that's the same on the top and bottom because that value is 1. So if I cancel those out, that leaves me with the 4 8s. 1, 2, 3, 4. I'll write that as 8 to the power 4. So what can we see here? What is the pattern? What rule is developing? Let's have another go. Okay. Let's change the base just for fun. Okay, here we go, 4s. 4 to the 7 divided by 4 to the 4. Write it as a fraction. 4 to the 7 over 4 to the 4. Let's write them out. I've got 7 4s on the top, 4 4s on the bottom. What can I cancel? I can cancel out all of these. Anything on the top is the same as anything on the bottom. The value is 1. What does that leave me with? In this case, it leaves me with 3 of the 4s, which I write as 4 cubed. What is the pattern? Where are we going here and what is the rule? Well, what we can see here is we had 7. We took away the 4 that was on the bottom. We were left with 3. So that is the rule there. The rule comes down to a subtraction. So here in the multiplication, when we multiplied, we added. Down here in the division, when we divide, we subtract. Okay, remember the bases have to be the same. So let's just have a look at a few questions on that. Okay, let's do this one. This one. This one. Okay, here we go. Multiplying. Firstly, check the bases are the same. They are. Okay, so if we're multiplying, then we can do that thing that we saw before. We here have 5 to the 2 times 5 to the 12. We could use our multiplication GeoGebra to help us with that. Let's see if we can get a 5. There, oh, I had it. There we are, 5. Okay, so the question is 5 to the 2 times 5 to the, oh, we don't fit it on. We'll have to draw it by hand. 5 to the 12. Okay, so if we're doing 5 to the 2 times 5 to the 12, then we need 2 more 5s here, don't we? 1 and 1 more, 2. Okay, that gives me 5 to the 2, and there's 12 of them, which gives me a total of 14. Okay, or we could use the rule. The rule straight away would say, clear that. 5 to the 2 times 5 to the 12 is 5 to the power of 2 plus 12. What is 2 plus 12? 14. Okay, let's try again. 4 to the 3 times 4 to the 2. Again, check the bases are the same. They are. So I can apply the rule, which is 4 to the power of 3 plus 2. It wants us to evaluate it. Oh, it's a bit tricky, isn't it? 4 to the power 5. Okay, so you can do one of two things here. We could use the index laws and get 4 to the 5, and then on your calculator, you'll have a little power button. Most smartphones, when you turn your phone sideways, you'll have a little power button. It'll be like a X to the little Y. So I can do that on mine, 4 to the 5, and it gives me the answer of 1024. So I could press enter there, that would be fine. But because I'm evaluating from the beginning, maybe it makes more sense to sort of split it out and make it smaller. Maybe you don't have a power button. Maybe you want to do it by hand. So let's have a look at what this means. This would be 4 3 times, and then another 2. This is what we need to evaluate. So then you start evaluating. 4 4s are 16. Then what? Well, what is 16 times 4? Yeah, that's right. 16 times 4 is 64. Maybe then you want to multiply that by 4. 64 times 4 is 256. 256 times 4 is 1024. Again, it doesn't matter which way you went about it. The index law was 4 to the 5. We could type that in our calculator straight away and get 1024. Okay. Fill in the blank line to make the equation true. So this is testing our knowledge of the rule. Firstly, are the bases the same? Yes. Okay. We're multiplying, which means we need to add those first 2 indices to get the second. So this is saying if I had 12 lots of the 5 written out, how many more do I need to have 14 of them all together? So the answer there is 2. Well, these numbers are getting crazy. 13 to the power 49 divided by 13 to the power 18. Well, the good thing is it doesn't matter what the actual numbers are. We need to check 2 things. Firstly, are the bases the same? Yes, they are. And then we need to know am I multiplying or dividing. In this case, I'm dividing. So this is the same as 13 to the power of 49 divided by 13 to the power of 18. Remember, dividing means on a fraction. And then we need to look at, well, what can I cancel out? Well, if we went back to our applet, there were 49 on the top and 18 of them on the bottom. So I'll be able to take 18 out of them. What that gives me is 13 to the power of, well, I had 49 and I had to cancel out 18. That's the rule. When I'm dividing, I subtract the powers. So I just need to know now what 49 minus 18 is. Okay, and that is 31. Okay. Right, here's another one. Check both powers the same, both bases the same. Yes, they are. I've got 11 and 11. Great. Now imagine that I had 7 of the 11s across the top and 3 on the bottom. Yeah, so then I'll be able to write them like this: 11 to the power 7 divided by 11 to the power 3. Okay, so imagine then I could write them out. But I could also use the rule. So that's 11 to the power of 7 minus 3. Because I'm dividing, I can subtract the powers because you're cancelling them out. So 7 minus 3 is 4. Okay, so hopefully that filled in a few gaps. I know we moved very fast at the end there, but hopefully I've filled in those for you and you've got those applets to have a play with. So all the rules are in the textbook, on the lesson page. They're summarised. So you'll be able to see all of those lessons there, the rules there. When you're multiplying, you add them. When you're dividing, you subtract them. And they talk about the power 0, which we talked about before with the applet. So I hope that fills in the gap. I'm really glad you stuck by me and you hung through to the end of the credits and you got to see bonus material. Anyway, again, thanks for tuning in today. Hope you enjoy the help that we can offer and that we see you again next time. Cheers. Bye now.